This is problem 432. It's on page 176. Helium is to be compressed from 120 kilopascals and 310 Kelvin to 700 kilopascals 430 Kelvin. A heat loss of 20 kilojoules per kilogram occurs during the compression process. Neglecting kinetic energy changes, determine the power input required for a mass flow rate of 90 kilograms per minute. Well, let me draw a compressor the way we normally draw them. We've got helium coming in and leaving, not hydrogen, helium. The helium is compressed because there's shaft work coming into the compressor, causing the energy of the helium to be increased as it flows through the compressor. We call the entrance section 1 and exit section 2. Then the temperature at the exit is 430 Kelvin and the pressure at the exit is 700 kilopascals as we were given. The pressure at the entrance is 120 kilopascals. The temperature at the entrance is 310 Kelvin. Now, they told us that there was heat loss, and that heat loss was 20 kilojoules per kilogram. What symbol should I use for that heat loss? Q, good. Is it a Q, capital Q, lowercase q, Q dot?
The big Q dot.
A big Q dot. Now be careful. It is kilojoules per kilogram. In fact, it's 20 of them, right? 20 kilojoules per kilogram. This is a per unit mass property or per unit mass thing. So it's a specific thing,
Oh, okay.
right? That's why we actually have to use little q. It's not a dot because it's not a per unit time thing. Okay, but it's anytime you see a per unit mass, think little letters. Okay?
Oh,
So Q is 20 kilojoules per kilogram. So what does that mean? That means that every kilogram of helium that flows through this system loses 20 kilojoules of heat. That's what it means. Right. If 100 kilojoule or if 100 kilograms of helium flows through this thing, how much heat is lost? 100 times 20, 2,000. Right? 100 kilograms flows through, well, 2,000 kilojoules is lost. Where do you think that heat comes from? Well, if the helium leaves with more energy than it came in with, then this heat loss must come from the shaft work. So the shaft work is not only compressing the helium, but providing for the heat loss. Okay? Now there's one more piece of information, and that is that the mass flow rate flowing through this thing is 90 kilograms per minute, 90 kilograms per minute. Now you guys probably don't have a real good feel for kilograms, but 90 kilograms, how much weight are we talking about there?
140 pounds.
a lot.
I think more like 160 or 70 or 80, isn't it? I don't have a real good feel for it.
10.6.
Because is it 1.6 or 2 point something? I can't remember. We could figure it out. But
Heavy.
what's that?
It's heavy.
It's 2.2.
2.2. So about 2.2 times this will be the weight flow rate through this, essentially, right? So that's a couple hundred pounds, right? Can you imagine a couple hundred pounds of helium flowing through something every minute? I mean, helium is not all that dense, especially at 120 kilopascals, roughly atmospheric pressure, and 310 Kelvin, roughly atmospheric temperature. That's not very dense helium, right? You can fill a balloon and it would float away. So if we've got a lot of weight flowing through, this is a heck of a compressor, which we're going to find out here in just a minute. Okay. Now, how are we going to find that out? Well, we're supposed to find how much shaft work this would require. Why would we be interested in the amount of shaft power required?
You're looking to move a whole lot of helium.
We want to move a whole lot of helium. We want to find out how much it would cost, right? Because we're probably going to hook up an electric motor to this thing, and we want to know what the power company is going to charge us to compress as much helium. Okay, this may be a very good parade balloon filler, okay? You know, the big floats and things that they have. This may be pretty good for this. In fact, I think it would fill it pretty quickly. But anyway, so how are we going to solve this? Well, notice we're asking about something that has to do with energy or power, so we should probably use an energy balance. Okay? Now, let's be a little bit careful here. I derived an equation for you, and it looks something like this. It said that the shaft power for a compressor would just be equal to, let's see, the mass flow rate times the change in enthalpy, H2 less H1, because let's see, the enthalpy coming in would be less than the enthalpy exiting. Is that equation right? Probably not the way you asked it is not right.
Because you have a heat loss in there too.
You got a heat loss, right?
Yeah.
So this equation doesn't account for that heat loss. So we've got to go back to our original energy balance equation for a steady flow system. This may look a little bit different than the steady flow energy balance that you have written down in your book, but that's because I've removed the summation signs. There's no need for the summation signs because there's just one entrance and one exit. Okay. I've also automatically just neglected kinetic and potential energy changes. Okay, so I'm not worried about 2 being higher or lower than 1 or the change in velocity. I'm not really worried about that part.
Enthalpy has heat in it, but this is an additional heat loss.
Q is this heat loss. Don't think of enthalpy as a heat loss.
Not heat loss, yeah.
Okay? Enthalpy is not a heat loss. Enthalpy has to do with the energy of the flowing stream
Okay.
in its thermal and flow forms. So we wanted to find out how much shaft work. Well, work going into a system is negative, right? So Q dot less negative shaft power going in equals M dot H2 less H1. I'm going to use an energy balance to say that the mass flow rate at the exit and entrance are equal. Right? Now, does this negative of a negative confuse you? This is just a sign convention. This negative comes from here. It's just the negative from the energy balance equation. This negative comes from the fact that I know already the direction of the work is into the system. Therefore, that is a negative thing. If I hadn't put this negative sign on, everything would still come out all right. I would just calculate a negative shaft power and realize, well, that means it's flowing in. Okay? I already know that. It's kind of like when you assume a direction for force in statics. If you really already know the direction of force, you're going to assume the right direction. Okay? All right, so the shaft power then, solving for it, would be equal to the mass flow rate times the enthalpy change less Q dot. Now we have to be a little bit careful there. Because wait a second, we haven't evaluated Q dot yet. Remember there's a sign associated with that as well, right? Heat flow in, is that positive or negative? Positive. Heat flow in is this heat flowing in or out? It's really out, right? So actually, I should have done something like this, negative Q dot out, right? And that would make it positive Q dot out here. Make sense? The sign can be really confusing. That's why I went through this with you. Hopefully it makes more sense now. Now, this actually makes a lot of sense. It says that the shaft power has to provide the energy change of the helium as it flows through the compressor and has to provide the heat loss. And that's what we already discussed and said. So the energy balance actually matches with what our intuition says has to happen here. Okay. So let's see what we get from this. The mass flow rate is not, well, wait a second, before we plug in numbers, do we have the enthalpy at the entrance and exit? No, we don't. We have temperatures though. Is there a way we can use that? Yeah. How about if we just do another CP delta T trick? Okay? They're just approximating the enthalpy change as CP delta T.
So our little q is going to equal our q dot this time?
Good question. Will little q equal q dot? Well, we've got another problem there, right?
Yeah.
So how are we going to relate little q to q dot?
We need to do it.
Well, think about it this way. If you had a bucket brigade, okay, you got so many buckets flowing by per time and each one carried a certain amount of water, couldn't you calculate the flow rate by just multiplying the volume that each one carries by the flow rate of the buckets? That's all we're going to do here. Each bucket, in other words, each kilogram, carries 20 kilojoules out. So if we multiply the number of buckets per time times the amount of energy each bucket carries, or loses really, then we've got the heat flow rate. So what I've just said is this is simply m dot little q. That's all it really is.
Okay.
All right, so let's plug in numbers. So the mass flow rate, I guess we could, well, let's not. The mass flow rate is 90 kilograms per minute. And then I need the heat capacity of helium. If you look up the heat capacity of helium, you'll find it's 5.1926 kilojoules per kilogram per Kelvin. And then you need the temperature change. T2 is 430, T1 is 310, and that difference is in Kelvin, 4 degrees Celsius, because it's just a difference in temperature. That takes care of this first bit here. But then we need to add to that. Now, if I leave this, if I pull this little Q inside of that, would it make sense to you? In other words, if I just factor out this mass flow rate and leave it here. So I'll just put the little Q right here, 20 kilojoules per kilogram. Okay, this is still m dot Q, right? I just put it inside of the bracket so I didn't have to write that Q, that m dot
Okay,
twice.
yeah.
Okay. Notice the units are the same, kilojoules per kilogram, so I know that everything's okay. So anyway, this comes out to about 57,880 kilojoules per minute. Now you probably don't have a real good feel for kilojoules, and you don't know if this is big or small. So let's find out. Well, let's see, there's 1 minute per 60 seconds. So what is a kilojoule per second? It's a kilowatt, right? Because a joule per second is a watt, so a kilojoule per second is a kilowatt. This comes out to a mere 965 kilowatts. Now, to put that in perspective, that is about it's exactly 0.965 megawatts. Power plants are measured in megawatts, okay? Now, a power plant will put out a whole lot more than a megawatt, but remember when we went and visited the Ohio River, can't think of the name, the hydro plant, thanks. You remember how much power each one of those turbines put out?
Like 1 point something?
It was like 12 or so. Okay, so it's about 10 to 12 megawatts. We're taking 1/12 of one of those, one of those turbines' power output. That's quite a bit. A steam-powered turbine typically outputs about 250 megawatts. So this is a heck of a compressor, to say the least.
That's a lot of light bulbs.
That's a whole lot of light bulbs. That's a whole lot of homes. Okay. If you drew 4 kilowatts at your home continuously, you'd have an electric bill that's about 4 times what you're used to. Most homes draw about a kilowatt or so on average. So this is 965 homes, basically, almost 1,000 homes. All right, any questions?
Is that normal though? Would you see that?
Would you see something like this? No, I think the problem was made up pretty badly. That's what I think.
Let's say, I remember, we were at a factory last day, installed some brand new machines, and they were only allowed to run at night.
Yeah.
Because just the machines in the factory, which didn't take up a whole lot, they pulled so much.
Yeah, yeah. Electricity for you and me as residential consumers does not depend on the time of day that we buy it. But for industrial customers, it depends on what time of day they buy it, and that's why they want to buy electricity at night if they can. So, anything else?